In 1980, a student walked into a campus doctor's office at the University of Sheffield. He wasn't worried. It was something minor, but the doctor noticed something odd. The student's head was slightly larger than normal, so they referred him to a specialist. And when the specialist looked at the scan, he went quiet, because what should have been a brain was mostly fluid. The student had an IQ of 126, a first-class honors degree in mathematics. No symptoms, no problems. He had, for all practical purposes, no brain. And somehow, he was one of the smartest people in the room. To understand how this is possible, we need to go back to a man named John Lorber. Lorber was a British neurologist, meticulous, methodical, the kind of scientist who didn't make claims unless he had data to back them up. Throughout the 1970s, he studied a condition called hydrocephalus. Hydrocephalus, sometimes called water on the brain, is when cerebrospinal fluid builds up inside the skull. Normally, that fluid cushions the brain, but when it can't drain properly, the pressure builds, and it slowly, silently destroys brain tissue from the inside out. Most children diagnosed with it don't survive infancy. Those who do are often severely disabled. But Lorber kept seeing something that didn't fit. Some of his patients whose scans showed massive fluid buildup, patients who should have been profoundly impaired, were fine, more than fine. So he started documenting over 600 cases, systematically, carefully, and he divided them into groups based on how much of their skull was filled with fluid. In the most extreme group, where fluid occupied 95% of the cranial cavity, he expected the worst. What he found instead would change neuroscience forever. The Sheffield student was referred to Lorber almost by accident. A campus doctor, treating him for something unrelated, noticed his head was slightly larger than average. A minor observation, easy to overlook, but Lorber ran a CAT scan. The normal human brain fills the cranial cavity to a depth of about 4–5 centimeters of tissue. This student had less than 1 millimeter, not 50% less, not 20% less than 1 millimeter of cerebral tissue, a thin ribbon lining the inside of his skull. Everything else, fluid. And yet, IQ of 126, upper range of gifted, first-class honors degree in mathematics, socially normal, no symptoms, no complaints. Lorber, who rarely used dramatic language, described it simply: the boy has virtually no brain. In December 1980, science writer Roger Lewin published an article in the journal Science. The title was a question: is your brain really necessary? It wasn't rhetorical. He genuinely didn't know the answer. You might think this was a one-time anomaly, a statistical fluke, an error in the scans. But in 2007, something almost identical happened again. This time in France. A 44-year-old man went to the hospital in Marseille. His complaint: mild weakness in his left leg. 2 weeks. Nothing alarming. Doctors ran an MRI. What they saw stopped them cold. Dr. Lionel Fouillet, the neurologist on the case, later said, "We were very surprised when we looked for the first time at the CT scan. The brain was very, very much smaller than normal. The man's skull was filled with fluid. His lateral ventricles, the chambers that hold cerebrospinal fluid, had expanded so massively that they had compressed his brain into a thin outer layer. His cortex, the seat of thought, language, personality, consciousness, existed as a narrow rim around the edges of his skull." The paper published in the Lancet was titled, almost ironically, "Brain of a White-Collar Worker," because that's exactly what he was. Married, 2 kids, a job as a civil servant. He had spent 44 years living, working, laughing, raising a family with a brain that, by every textbook definition, should not have been able to do any of that. His IQ, 75. The low average, but functional, competent, normal enough that no one ever suspected anything was wrong. Not him, not his family, not his doctors until they looked. And after treatment, the leg weakness resolved. The scans didn't change. The fluid stayed. The missing brain stayed. And so did he. Here's where it gets complicated, because neuroscience has 2 ways to respond to a case like this. The first response is to explain it away. The brain was compressed, not destroyed. Those neurons were still there, just squeezed. And that may be true, to some extent. but it doesn't fully explain the Sheffield student. 1 millimeter of cortex is not just compressed tissue. It represents a radical loss of neural architecture, and it doesn't explain the consistency. Lorber documented 600 cases. In the most severe group, half the patients had IQs above 100. That's not a fluke. That's a pattern. The second response, the more uncomfortable one, is that we fundamentally don't understand how the brain works. Cognitive psychologist Axel Clearmans put it directly. One of the key takeaways is that plasticity likely extends far beyond our previous understanding. It's truly remarkable that the brain can maintain functionality, more or less, within the expected range, even with potentially far fewer neurons than in a typical brain. The key word is plasticity. When the brain is damaged slowly over months, years, decades, it doesn't just break. It adapts. It rewires. It reroutes. It finds other ways. The Sheffield student's brain had been compressed since before he was born. It had a lifetime to reorganize, to compensate, to build new pathways where old ones were lost. It's the same principle behind why stroke patients can relearn to speak, why people who lose a limb can remap sensation, why the brain, after catastrophic damage, sometimes recovers in ways that defy expectation. But here's what makes the hydrocephalus cases different. In a stroke, there's a scar. There's dead tissue. There's a visible wound. In these patients, there's just absence. And the brain, somehow, still ran. Which forces a question that neuroscientists are still arguing about today. If the brain can do this, if it can compress, adapt, and survive at a fraction of its normal volume, then how much of what we think is essential actually isn't? Animated diagram of a normal brain versus hydrocephalic brain. Takeaway. The deeper question. Scripts. We like to think we understand the brain. We have maps of it. We've named every region. We know that the frontal lobe handles decisions. The hippocampus handles memory. The visual cortex processes what we see. And then a student walks in with a math degree and no cortex, and the map falls apart. What the hydrocephalus cases really reveal isn't just that the brain is resilient. It's that our model of consciousness, this idea that specific thoughts live in specific places, that a certain volume of tissue is required for a certain level of intelligence, is almost certainly too simple. Clearmans says something that stays with me. One idea I'm defending is that awareness depends on the brain's ability to learn, not on its size, not on its structure, on its ability to adapt. If that's true, then the Sheffield student wasn't an anomaly. He was a proof of concept, a living demonstration that the thing we call mind is more flexible, more distributed, more mysterious than we've been willing to admit. The man with no brain graduated, got a job, lived a life, and the question he left behind, the one Roger Lewin asked in 1980, and that nobody has fully answered since, is still sitting in the back of your mind right now. Is your brain really necessary? Maybe the more honest answer is, we still don't know. If you want to go deeper on how the brain adapts and the cases that challenge everything we think we know about consciousness, there's a lot more on this channel. And if this is the kind of question that keeps you up at night, you're in the right place.